Our current understanding of the cosmos is just scratching the surface, and the complexities of nature surpass any predictions. Recently renowned astrophysicist Neil deGrasse Tyson made an assertion suggesting an undisclosed lunar information stemming from Japan's unmanned Lunar mission.
If you wanted to fake the moon landing, you would have to fake all of these documents. And it just seems to me it's way easier to just go to the moon.
This revelation prompts inquiries regarding potential information that NASA may not have disclosed. In this investigation, we delve into the cosmic interest sparked by Tyson's statement and unveil the mystery surrounding Japan's lunar findings. Join us as we unveil how Japan finally found what NASA was hiding on the moon. Japan joins elite lunar explorers with SLIM. Japan's unmanned lunar mission achieved an unexpectedly impressive feat, shedding light on the moon's origins. The spacecraft successfully gathered and transmitted data from analyzing 10 lunar rocks, marking a historic moment with its precise upside-down landing on January 20th. Despite the solar panels initially being blinded by the sun and temporarily shutting off communication with Earth, they were reactivated on the 8th day, allowing the spacecraft to reconnect with the Earth-based JAXA command center. Upon touchdown on the moon, the smart lander, known as SLIM, spent 4 days examining lunar rocks using its multi-band spectral camera to determine their composition. A black-and-white photo of the 6 rocks on the uneven lunar surface was relayed shortly after SLIM's reactivation. The rocks were named after dog breeds such as Akita Inu, Beagle, and Shiba Inu. Scientists believe that analyzing these rocks may offer clues about the moon's birthplace. Comparing the mineral compositions of moon rocks and Earth rocks is one method to investigate if they share similar elements. The giant impact theory suggests that a smaller mass spun off Earth during a collision with another celestial body, leading to the moon's formation. The data collected from 10 rocks was a cause for celebration for the JAXA team, who initially expected SLIM to examine and analyze only 1 rock. This information inspired the team to explore the moon's origins further. With this successful mission, Japan joins the ranks of the world's spacefaring nations that have reached the moon, following the United States, the Soviet Union, China, and India. The lander brought along 2 small rovers, each showcasing innovative moon mobility technology. One rover, equipped with a camera and scientific tools, utilizes a hopping mechanism for lunar movement. The second rover, a hand-sized sphere, was collaboratively developed by the government, private sector, and academic institutions. It rolls on the moon's surface, capturing images with a navigation system relying on eyesight. These photos were promptly compared to maps created by JAXA, displaying lunar crater patterns based on past flight data. Precision landing technology enables agencies to safely navigate and explore resource-rich regions, avoiding potential risks. Beyond local benefits, these achievements also have geopolitical implications, contributing to countries' positioning as global leaders in space exploration. Notably, the recent success of Japan's moon landing, despite challenges with the mission's solar panels limiting the time frame, underscores JAXA's significance in the global effort. This comes in the wake of other lunar attempts, including India's historic Chandrayaan-3 lander reaching the South Pole on August 2023, making India the first country to land on the moon since China in 2020. This mission involved 3 key components: the orbiter, positioned in lunar orbit to scrutinize the moon's surface and atmosphere; the lander, named Vikram, tasked with collecting data on temperature, seismic activities, plasma density, and surface composition; and the lunar rover, Pragyan, designed for autonomous exploration. The orbiter, equipped with advanced scientific instruments, played a crucial role in gathering comprehensive data from a circular orbit around 100 kilometers above the Moon's surface. The lander, paying homage to Dr. Vikram Sarabhai, the founder of the Indian Space Research Organization, successfully executed a controlled descent to the challenging lunar South Pole. Vikram's precision in navigating extreme environmental conditions showcased India's technological prowess and expertise in orchestrating complex lunar operations. Upon landing, Vikram deployed solar panels essential for powering its scientific instruments and established a crucial communication link with the orbiter. Real-time communication facilitated the exchange of data, enabling scientists on Earth to monitor and analyze lunar activities. The subsequent phase involved the deployment of the lunar rover Pragyan, equipped with cameras and sensors for autonomous exploration. The Chandrayaan-3 mission commenced on July 14, 2023, with a strategic orbital dance around Earth, gradually accumulating momentum. On July 21, the spacecraft transitioned to the lunar phase, and precise orbital maneuvers by the ISRO team positioned Chandrayaan-3 in an optimal circular orbit around the Moon by August 19. The lander Vikram, detached from the orbiter on August 23, executed a controlled descent, overcoming challenges akin to a tightrope walk from space to the lunar surface. Unveiling the Moon's secrets in just one Earth day, Vikram's descent involved deceleration from a brisk speed of 1.68 kilometers per second, precise adjustments to trajectory and orientation, and positioning between two lunar craters. The chosen landing site, Simpelius N and Manzinus C, presented extreme conditions with temperatures as low as -240 degrees Celsius and sporadic sunlight. Vikram's successful landing underscored India's capability to conduct sophisticated lunar operations in demanding environments. The subsequent deployment of Pragyan, the autonomous lunar rover, marked the beginning of the surface mission. With limited operational time equivalent to a single lunar day, Pragyan navigated the rocky and unpredictable lunar surface using onboard cameras and sensors. The rover's autonomy ensured efficient exploration without stumbling over obstacles or becoming trapped in challenging terrain. India's Chandrayaan-3 mission made waves by exploring the Moon's South Pole, achieving historic feats and surprising many with its cost-effectiveness. The mission's budget, of just $74 million, demonstrated India's ability to blend innovation with financial efficiency, notably outperforming its predecessor, Chandrayaan-2, with a significantly lower budget. Chandrayaan-3's financial success was attributed to its compact design and strategic use of existing technology. Weighing only 1.4 tons, the combined lander and rover were considerably lighter than their international counterparts, reducing launch and fuel costs. The mission efficiently repurposed the GSLV Mk3, India's robust rocket, and adapted designs from Chandrayaan-2, showcasing a prudent use of resources. Comparing Chandrayaan-3's budget to other lunar missions highlighted its cost-effectiveness. Russia's Lunar 25 had a budget nearing $2 million. NASA's Viper rover was projected at $433 million, and China's Chang'e 4 cost around $180 million. Chandrayaan-3's success was attributed to its lightweight design and strategic use of technology, setting an example for efficient space exploration. The mission faced numerous challenges, from achieving the correct lunar orbit to navigating the Moon's tricky terrain. The 17 minutes of terror marked the crucial phase when the lander, Vikram, had to slow down and land without real-time help. Successful, it allowed the rover, Pragyan, to explore the Moon's surface. Operating on a tight schedule of 14 Earth days, Both raced against time, facing extreme lunar temperatures, communication blackouts, and the constant threat of solar radiation. Chandrayaan-3's significance extended to its landing site near the South Pole, a challenging location with rough terrain and perpetual darkness. The mission overcame obstacles, making key discoveries such as variations in the Moon's exosphere and ionosphere. The lunar topsoil's thermal insulation potential suggested it could be used to build habitats, shielding astronauts from extreme lunar conditions. The mission also detected a potential moonquake, hinting at internal lunar processes, and the Pragyan rover revealed the presence of various elements on the Moon's surface. You see, Japan's accomplishment follows 6 months after India's moon landing and a few weeks after a failed attempt by the US company Astrobotic, as well as unsuccessful attempts by Russia and the private company iSpace in 2023. Several countries, including the United States through its Artemis program and India, are making efforts to land on the Moon. India is particularly interested in the Moon's southern pole, which has a unique and untouched surface with craters, trenches, and pockets of old ice. The recent live coverage of a lunar landing attracted viewers from various nations, including India. Countries like India are contemplating sending astronauts to the Moon, driven by the remarkable opportunities it offers to educate the public, advance human technology, and gain a deeper understanding of our solar system. Irrespective of one's cultural or historical background, observing the Moon in the night sky prompts awe at the presence of a man-made spacecraft orbiting its surface. The Moon serves as an ideal arena for international collaboration or competition in a subtle yet significant manner. The heightened global interest in lunar exploration, involving countries and corporations such as the US, Russia, China, India, and Israel, provides ample opportunities to form new alliances. These partnerships connect individual researchers and organizations, fostering peaceful collaboration on Earth and enabling governments to achieve more in space by pooling resources. Some argue that lunar exploration can benefit the economy, with startups developing space technologies and contributing to missions. Notably, India has seen a rise in space startups. In the long term, economic advantages may arise from the Moon's water, helium-3, and rare Earth element deposits. Odysseus and Nova C unveil NASA's lunar payload bonanza. The United States continues to be the unquestioned leader in lunar and space exploration, despite recent setbacks such as the delay in NASA's Artemis mission. The Odysseus lunar lander recently achieved a significant milestone, marking the United States' return to the Moon after more than 50 years. Think of it as a lunar cargo mission. This accomplishment follows a less successful attempt by another US lunar lander. Odysseus, affectionately nicknamed Odie, stands out as an unconventional spacecraft created by Intuitive Machines, a team specializing in commercial lunar missions. Their goal is to deliver small packages, referred to as payloads, directly to the Moon. The last time a US spacecraft landed on the Moon was in 1972 with Apollo 17. Odie has now ended this long pause, and NASA invested an impressive $118 million in this lunar mission known as Commercial Lunar Payload Services. If you're wondering what a payload is, according to space experts at Ivona, it's a crucial part of a spacecraft dedicated to achieving the mission's primary goals. It could include scientific instruments, communication devices, or other specialized equipment. Meet the Nova C, the flagship model of the lunar lander accompanying Odysseus. Described by Intuitive Machines as roughly the size of a British telephone booth with legs, NASA adds that it's a hexagonal cylinder measuring 4.0 meters tall and slightly over 1.5 meters wide. Odie is not carrying snacks, but is loaded with 5 NASA payloads and 1 from a commercial partner, totaling an impressive 220.462 pounds or 100 kilograms. Hold onto your space helmets because NASA's cargo for this lunar journey goes beyond typical equipment. Picture tools for communication, advanced navigation devices, and gear designed for accurate landings. Plus, there's valuable information about rocket exhaust and moon surface activities. Don't forget the intergalactic weather report and its impact on radio astronomy. According to Joel Kearns, NASA's Science Mission Directorate Deputy Associate Administrator, this mission is essentially a space delivery service. NASA is investing in this space exploration, essentially saying, take our gear, place it on the moon, and bring us back the details. It's like ordering a package, but instead of a delivery person, we have a whole lunar lander making a special run. And guess what? It's not just scientific equipment on board, they've added a touch of art and technology. American art maestro Jeff Koons has contributed a small box to the mix. What's inside? 125 shiny steel balls, each representing a different moon phase over a month. Koons aims to honor historical figures through his artwork, connecting it to the achievements of past legends. So, it's not just about data. It's a cosmic celebration of human accomplishment. Odysseus landed on the moon precisely at 6:23 p.m. EST or 23:23 GMT on a Thursday, making a notable entrance into the cosmic scene. This lunar mission was initiated by SpaceX using their reliable Falcon 9 rocket, which took off gracefully from NASA's Kennedy Space Center in Florida on February 15. Picture Falcon 9 propelling our lunar explorer into Earth's orbit at speeds exceeding an astonishing 24,854.84 miles per hour. That's like a thrilling SpaceX roller coaster ride in space. After an exciting 48-minute journey, approximately 223 kilometers or 139 miles above our planet, the rocket smoothly separated from our lunar companion, Odie. Now, bidding farewell to its booster buddy, Odysseus was left to navigate the vastness of space independently. Talk about self-sufficiency. Equipped with an onboard stellar map, Odysseus had a navigation strategy to traverse the cosmos. Aligning its solar panels with the sun's rays, it intelligently recharged its batteries, preparing for its lunar adventure. If all goes well on its lunar journey, this hexagonal marvel will spend a solid 7 days exploring the moon, diligently working until the lunar night falls. When the night sky takes over, Odysseus, the hard-working explorer, takes a well-deserved nap in sleep mode. Now, covering an impressive 400,000 kilometers or 250,000 miles in its journey, Odysseus began a dramatic 73-minute descent to the lunar surface. CEO Stephen Altimus from Intuitive Machines stated at the beginning of the mission that they had an 80% chance of success. Shortly before the spacecraft landed, the laser navigation system experienced a temporary issue. However, the Intuitive Machines flight control team quickly adapted by switching to NASA's navigation Doppler LiDAR, leading to a last-minute route adjustment around the moon. Prasoon Desai, NASA's Space Tech Mission Directorate Deputy Associate Administrator, revealed that the navigation Doppler LiDAR, initially intended as a tech demo, became the primary system for velocity and altitude information during the mission. Following this tense moment, the true suspense unfolded after Odysseus successfully landed. Radio silence from the lunar surface raised concerns about the lander's status. A sense of relief swept over when a communication link was established, connecting Odysseus with the control team on Earth after some troubleshooting. Within a few hours, Intuitive Machines shared the positive news that Odysseus was upright and transmitting data, accompanied by captivating lunar images. The new space race. This lunar lander isn't just delivering things to the moon. It's on a mission to gather important information about the moon, especially at its southern pole. This is all part of NASA's big plan for a crewed mission in September 2026, featuring Artemis 3. The focus on the southern pole is because there's a possibility of finding water ice there. Before sending astronauts to this cold lunar spot, NASA is being smart by collecting more information. They want to know how much water is there and how accessible it is. Water on the moon is crucial for future lunar explorations. NASA's vision goes beyond a short visit to the moon. They aim to establish a permanent lunar base on the southern pole, and that's just the beginning. The moon is seen as a launching pad for an even more ambitious goal, Mars. Sue Lederer, the person in charge of the Commercial Lunar Payload Services project at Johnson Space Center in Houston, explained in a press conference that NASA's new strategy involves exploring the moon for Artemis and reshaping their approach. Essentially, NASA is looking to establish a lunar economy, envisioning a space marketplace where private companies compete to be part of lunar exploration. According to Ali Bramson, a planetary scientist at Purdue University, there's still a lot we don't know about the moon, from how it formed to the technologies needed for exploration and sustaining life on its surface. NASA is on a mission to unravel the cosmic puzzle, moving beyond just planting flags and footprints. The goal is to shape a future where the moon serves more than a celestial nightlight. It becomes the launch pad to the stars. Exciting news is spreading globally as countries engage in a modern race to explore the moon. JAXA has collaborated with the United States to develop a pressurized lunar rover, a crucial element of the Artemis missions for future manned flights to the moon. This advanced technology is essential. Nowadays, more countries are actively involved in space exploration compared to a few decades ago. This is especially evident in satellite missions, where over 60 countries have participated in gathering data or images of Earth. This trend is now extending to moon exploration. The motivations for focusing on the moon are similar to the original space race in the 1960s, showcasing technological prowess and inspiring the younger generation and the wider public. The difference this time is the involvement of more than 2 superpowers. With numerous participants, there is still competition, but there is also an opportunity for collaboration, forming new international alliances to study space. Thanks to the involvement of many countries and technological advancements over the last 60 years, there is potential for more sustainable exploration. This may include establishing permanent settlements on the moon, utilizing its resources, and in the long run, creating a tourist industry or mining lunar deposits for profit. South Korea's Pathfinder lunar orbiter is currently studying the moon's surface to find potential landing sites. India's Chandrayaan-3 rover is near the South Pole, and the Capstone spacecraft, developed by a space startup with funding from NASA, as well as NASA's Lunar Reconnaissance Orbiter, are also nearby. The Lunar Reconnaissance Orbiter collects information about the moon and creates maps for future landing missions. Meanwhile, the Capstone spacecraft is investigating the stability of a unique lunar orbit. Despite the Chandrayaan-2 rover from India crashing, the orbiter carrying it is still operational. China's Chang'e 4 and Chang'e 5 lunar landers are still in operation, with efforts from other countries and businesses to join the lunar exploration. Even though the Lunar 25 mission crashed on the moon 3 days before the Chandrayaan-3 landing, it is still noteworthy that Russia successfully created the rover and came very close to achieving its goal, moon mining renaissance. Exploring the moon can open up exciting opportunities for both scientific discovery and economic growth. Lunar materials like the readily available regolith hold the potential to support various activities in space. By melting regolith, we can create materials for radiation protection, micrometeoroid shielding, and even construction purposes. Additionally, extracting oxygen from lunar regolith oxides can serve as a valuable source of metabolic oxygen and rocket propellant oxidizer. Water ice on the Moon presents another valuable resource, offering potential benefits for radiation shielding, life support, and as a feedstock for oxygen and rocket propellants. Permanently shadowed craters may hold volatiles such as methane, ammonia, carbon dioxide, and carbon monoxide. These resources can further enhance the feasibility of sustained exploration and utilization of cislunar space. Moreover, the Moon's diverse minerals in its regolith offer the possibility of extracting metals and other elements for local industry. However, challenges exist, such as the Moon's scarcity in carbon and nitrogen, and uncertainties regarding the distribution and concentrations of various elements. Ongoing lunar exploration efforts aim to uncover additional economically valuable materials, with their exploitation dependent on their perceived value and the available energy and infrastructure for extraction. Successful in situ resource utilization, ISRU on the Moon relies on strategic landing site selection, surface operations, and the development of suitable technologies. Space agencies are actively scouting resources from lunar orbit, utilizing landers and rovers to investigate potential concentrations in situ. The Moon also holds a treasure trove of resources like solar power, oxygen, and metals. Elements such as hydrogen, oxygen, silicon, iron, magnesium, calcium, aluminum, manganese, and titanium abound on its surface. Notably, oxygen, iron, and silicon are particularly abundant, making up a significant portion of the lunar regolith. Research from Apollo 17's lunar atmospheric composition experiment reveals trace gases like hydrogen, helium, argon, and possibly ammonia, carbon dioxide, and methane in the lunar exosphere. Various processes such as solar winds reacting with the surface, lunar regolith evaporation, material deposits from comets and meteoroids, and lunar interior outgassing contribute to these trace gases. Although present in low concentrations, they are unlikely to be useful for practical utilization. On the Moon, daylight spans about 2 weeks, followed by an equal duration of night. Interestingly, the lunar South Pole has crater rims perpetually bathed in sunlight, while their interiors remain in constant shade. Innovative methods involve creating solar cells directly on lunar soil using a medium-sized rover. This entails heating the regolith, evaporating semiconductor materials, and depositing metallic contacts to form a complete solar cell array. However, this process requires importing potassium fluoride from Earth for material purification. The kilopower nuclear fission system presents a promising solution for generating reliable electric power on the Moon, Mars, and beyond, especially in areas with intermittent sunlight. While uranium and thorium exist on the Moon, importing nuclear fuels from Earth might be more cost-effective due to their high energy density. Radioisotope thermoelectric generators, relying on the natural decay of radioisotopes, have been utilized on the Moon for decades. Although typically sourced from Earth, plutonium-238 or strontium-90 could be produced on the Moon, potentially addressing concerns about accidental material distribution. Despite being a theoretical resource, helium-3 has garnered attention for nuclear fusion, but practical challenges persist in harnessing usable energy from this source. The lunar regolith, the Moon's surface layer, is abundant in elemental oxygen, constituting approximately 45% by weight. This oxygen is often found in lunar minerals and glasses with high iron content, such as iron oxide. Notable examples include ilmenite, olivine, pyroxene, impact glass, and volcanic glass. Different isotopes of oxygen, including 16O, 17O, and 18O, are present on the Moon. Several methods, about 20, have been proposed for extracting oxygen from lunar regolith. All these processes demand substantial energy input, ranging between 2 to 4 megawatt-years to produce 1,000 tons of oxygen. Interestingly, extracting oxygen from metal oxides yields useful metals, but using water as a feedstock does not. A potential method involves a two-step process. First, iron oxide is reduced using hydrogen gas to form elemental iron and water. Subsequently, water can be electrolyzed to produce oxygen, which can be liquefied at low temperatures and stored. The quantity of oxygen released depends on the abundance of iron oxide in lunar minerals and glass. Notably, oxygen production from lunar soil is relatively rapid, occurring within a few tens of minutes, while extraction from lunar glass takes several hours. Now it's time for today's subscriber pick. According to renowned astrophysicist Neil deGrasse Tyson, Japan finally found what NASA was hiding on the Moon. This came as Japan recently achieved an extraordinary feat by executing a highly accurate moon landing with their spacecraft nicknamed the Moon Sniper, touching down just a few meters from its intended target. This accomplishment made Japan the 5th country to successfully land a spacecraft on the lunar surface, joining the ranks of the United States, Russia, China, and India. The mission's goal was to land within an impressive 100-meter radius of its target, surpassing the typical precision of several kilometers. The chosen landing site was a crater believed to expose the Moon's mantle, a deep inner layer on the lunar surface. JAXA, Japan's space agency, shared captivating color images from the mission, showcasing the spacecraft positioned at a slight angle on the Moon's rocky gray surface, with elevated slopes in the background. JAXA remains optimistic about the mission's significance as it aims to leverage vision-based navigation to explore the Moon's potential water resources. This information is crucial for future lunar endeavors, including the establishment of a base as a potential pit stop on the journey to Mars. Japan's lunar achievement is part of a global resurgence in lunar exploration, with both governments and private entities launching new missions 5 decades after the historic human moon landing. Let us know what you think in the comments below. Prospects and challenges in harnessing lunar resources. Evidence gathered from multiple orbiters strongly suggests the presence of water ice on the Moon's surface, particularly concentrated around the South Pole. However, the correlation of results from different datasets is not always straightforward. Permanently shadowed lunar regions cover a cumulative area of 31,059 kilometers square, with 13,361 kilometers square in the northern hemisphere and 17,698 kilometers square in the southern hemisphere. The exact characteristics of these areas, including the presence, distribution, concentration, and depth of water ice, are not fully known. Therefore, more data is essential for designing extraction and processing systems. Water on the Moon may have originated from water-bearing comets, asteroids, meteoroids, or through in situ production from solar wind impacting oxygen-bearing minerals. The lunar South Pole, with crater rims exposed to constant solar illumination and permanently shaded interiors, could naturally trap and collect water ice for future mining. Water molecules on the Moon can be broken down into hydrogen and oxygen, forming molecular hydrogen and molecular oxygen, which can be used as rocket bipropellants or in metallurgic and chemical production processes. A joint panel of industry, government, and academic experts estimated a near-term annual demand of 450 metric tons of lunar-derived propellant, requiring 2,450 metric tons of processed lunar water, potentially generating $2.4 billion in annual revenue. Slopes facing the moon's poles exhibit higher hydrogen concentrations due to reduced sunlight exposure, preventing hydrogen vaporization. These slopes, particularly those near the poles, show about 45 ppmw of hydrogen. Various theories propose that hydrogen may have been deposited by comets and asteroids or formed through solar wind interactions with lunar surface compounds. Questions persist about the diffusion and utilization of bound hydrogen, which is crucial for propellant production and has various industrial applications, such as oxygen production through hydrogen reduction of ilmenite. While mining the moon or asteroids could be a substantial shortcut to achieving long-term habitability in space, there's a crucial consideration. Before initiating any mining operations, businesses and government agencies must determine whether it's more cost-effective to process the materials in space or transport them back to Earth. This decision hinges on the economic viability of mining various resources. At present, the feasibility may not seem worthwhile, and establishing proof of concept through decades of work may be necessary, considering the considerable logistical challenges of extracting materials from space's hostile environment. Starting with the inception of the Apollo missions many years ago, extensive research and innovation have been conducted to explore the feasibility of space mining. The initial serious consideration of utilizing lunar resources took place in November 1962, during a meeting focused on the Apollo mission planning. NASA recognized the necessity of a continuous oxygen supply for its astronauts and explored the option of extracting it directly from the lunar surface. This approach was driven by the exorbitant cost and energy associated with launching materials from Earth. The concept that essential materials should be sourced on-site has been present for a considerable period. However, during the brief lunar visits of a few days or hours, this idea was not implemented. NASA employs the term in situ resource utilization to encompass the broader process, as the term mining alone does not adequately capture the gathering and utilization of materials in space. ISRU involves mining the lunar surface for materials and resources, and then using these raw materials to manufacture new products. For instance, lunar geologists have substantial evidence indicating the presence of water reservoirs, potentially in the form of ice, in the permanently dark regions of the moon concealed beneath the surface. The Lunar Flashlight mission by NASA aimed to identify and catalog these reservoirs. Future lunar inhabitants could tap into these ice reservoirs, melting the ice to replenish their portable water supply. Moreover, the hydrogen and oxygen derived from the chemical splitting of this water on the moon could be utilized to create rocket fuel and propellant or provide habitable air to bases and shelters. Exploring the concept of ISRU, astronauts could extract metals like silicon, iron, titanium, and aluminum from lunar soil. These metals could be used in constructing housing and launch vehicles. Jerry Sanders, the lead of NASA's ice system capabilities at the Johnston Space Center, suggests that these metals can be obtained by extracting and refining them from regolith. Approximately 42 to 44% of the regolith consists of oxygen. Despite the EMUS-3 launch scheduled for 2025, NASA is already preparing for ISRU activities. The Lunar Trailblazer spacecraft, orbiting the Moon, will employ an infrared spectrometer to search for surface water ice. Similar to the Lunar Flashlight mission, scientists may use probing techniques to detect the quantity and distribution of these ice reservoirs, as water absorbs infrared light. NASA's Viper mission will directly investigate water ice by digging into the lunar surface. Thank you for watching. See you in the next update.